Okay, so good evening, everyone. This is our extra tutorial session today on 5th April for the NPTEL course on finite element modeling of welding processes. So today we would be, as discussed in the previous session, that we would be solving one problem in Phoenix, as we had discussed last time. So it's essentially a transient elastodynamics problem with Newmark time integration method, which happens to be a tutorial which is offered by Blair. Yeah. So I will just download this notebook. Is which packages have they used for visualization? Okay, it's map. Okay, fine. So yeah, so today we'll just review once first what the problem that we are solving. So I hope you are following, right?
Yeah.
Yeah. So it's essentially we are solving a problem, such this beam problem, right? Beam vibration problem. So in the previous tutorial sessions, we never, apart from one heat conduction problem, we didn't do any time-dependent problem in Phoenix, right? Which uses a Newmark beta time integration approach. So in this problem, so we have the elastodynamics equation, which combines the balance of linear momentum here, divergence of sigma plus rho into F vector is equal to rho u double dot vector, where u is the displacement vector field, a is the acceleration, rho is the material density, F is the given body force, and sigma is the stress tensor, and which happens to be related to the displacement through a constitutive relation, to constitutive equation. And the approach that we'll be doing is the material model will be isotropic linear elastic model. So at first, as in finite element method, what we do is we first construct a weak form of this equation. So this equation here is a strong form. So strong form is like the differential equation is what we call as strong form. And by strong form, what we mean is that there has to be a certain condition which is satisfied at every point in the body. So it's this differential equation which has to be satisfied at every point in the body, right? And the thing is, but we would like to say approximate our solution because it's tough to satisfy. I mean, to solve and to solve a problem for a generic body, it's not possible to actually solve it without using numerical techniques, and that's the reason we first convert this problem into a weak form, which means that we want to solve this problem in an approximate sense, that it need not be satisfied at every point in the body, but it should satisfy in an average sense over the body. And that's the reason we convert it into a weak form. For that, we take a test function and then multiply toward this differential equation with v, which is the test function here, and then which will satisfy the displacement boundary condition as we had discussed last time, right? That the test function has always to satisfy the differential equation. Sorry, the displacement boundary condition. So now what it clearly says, we multiply this equation here with v on both sides. And since this is a vector equation, so we'll have to take a dot product. So that's what we are doing. We are taking a dot product and then integrating over the domain. So it's like this, and this comes after some simplification. So should we do it on pen, on paper? What do you suggest?
Sure.
Getting this, I think that would be like.
We have done this. I don't know. Okay, please go ahead.
So I think that would be like a nice way to. Let me open the iPad. Let me open this. What is that presentation? Okay. So I'll just open so that welding is okay. Yeah. Okay, so I'll also join. Yeah. This, yeah. Okay, so I hope the screen is visible, right?
Yes, it is. Reviewing Phoenix package.
Yeah. So what we'll do is we'll just derive that. I think that is a very nice exercise. So the title, I'll just make multiple copies. Okay. So the title is to derive. And actually, this weak form is valid for any linear problems or even for nonlinear problems. Ultimately, because even for nonlinear problem, this is the format we write, right? Eventually, of the elastodynamics equation.
Okay.
And what you will see is this elastodynamics equation. This equation is valid for any loading scenarios, be it mechanical, non-mechanical, electrode, what do you call, magnetic loads. Any loads we can. It also that first. Let me write the strong form. So this is the strong form. So strong form is rho u vector double dot is equal to divergence of sigma plus rho f vector. Now you'll see that this equation is valid for any material eventually, because this follows from the quantum mechanics, right? Is the balance of linear momentum for any body, any body. So and then to complete the problem, say given this arbitrary body of with volume omega and the surface being parcel omega, then say on certain segment of this body is on certain certain region of the surface we are having, say, some tractions. So this will be like the area this will be area in which we are applying some traction T vector. And say there is also distributed load being applied, so F vector. And then on this segment, we will have, say, some displacement boundary conditions. So we'll call it parcel T U, sorry, parcel omega U. So this implies that it's displacement boundary conditions on this area, and on this area we are applying some traction boundary condition. So this is just a generic body. So to have this problem as a well-posed problem, we'll have to have, say, subject to, which are also essentially the boundary condition, that U vector on parcel omega T for U vector is equal to, or let me call any point in this to be X vector, right? So U vector at X vector is equal to U naught vector, isn't it?
Yeah.
For X vector. The thing is here, mind you, that we are finding a solution which is U vector is equal to U vector X vector comma T. Since this is a time, it involves both, right? So it will have initial conditions and also boundary conditions. So let me first have initial boundary conditions. That would make more sense. Like, so boundary conditions and then initial. So boundary condition means that U vector at X vector comma T is equal to some U naught vector at X vector for all X vector is an element of parcel omega S, parcel omega U, and then some traction vector T vector at X vector comma T. Let me call this traction as capital T, just not to confuse here. This will be equal to, and also here also the same thing. So is equal to some T naught, we can have this also T naught vector, and then X vector And even the thing is, we can even have this also as a function. Even boundary condition can also be a function of time. For all x vector is an element of partial omega traction, right?
Yeah.
And for initial conditions, since the order of derivative of in time derivative is second order, so we require two initial conditions, isn't it, to start the problem? So
Yeah.
the first problem is
Okay.
the first initial condition will be to have, say, u vector at x vector t is equal to some u1, let's call it some u1 of x vector. I'll just call it 0, right? Some u1 vector defined throughout the domain. This is for all x in the element of omega, including the closure. So I'll just put closure also. And then closure, you know that. So closure is the interior set plus the limiting point.
I know. It's
Yeah,
like
there is something
full,
we
it's
wanted
like
to
full,
discuss, right?
like with boundary, no closure, matlab.
Yes, yeah, with the limiting points, which is the boundary. Yeah. Omega union partial omega, right? And then you'll have u dot vector also at 0 to be some, say, let's have something called, say, even u2, let's call it, or anything. Yeah, maybe just something like this. It's also to be, this is also the same thing for all, for so this then closes our problem, right? This then we can, this now is a well-posed problem. So once we have the strong form, now we would like to derive weak form. For weak form, now we need to construct our sets. So what is test function? So test function is actually follows what we call function belonging to the variational space. Now in this case, we would allow only our variational space will only take into account the Dirichlet boundary conditions. It has to. So this is the Dirichlet boundary condition, DBC, and this is the Neumann boundary condition, NBC. So Neumann means anything which involves derivatives. Again, I think it also deals with the order of elliptic operator that we have. So ideally, say if our elliptic operator is, say, 2n of something, right? So then this 2n will be the order of elliptic operator.
Okay.
Elliptic operator. Then 0 to n minus 1, all the boundary conditions with 0, which follows from 0 to n minus 1, that is called Dirichlet boundary condition. Yeah, this is like in engineering, we hardly encounter beyond, say, fourth order, right? So it's just some arbitrary, just some classification of higher order. So then till n 2n minus 1, this will be called Neumann boundary condition. So the moment we get confused what to call it, Dirichlet or this one, so then we have to, and you will see that engineering problems in general, the elliptic order will always be even ordered. So even in heat equation, you see that Laplacian operator, right?
Yeah, it's even.
Yeah, and when we deal even with, say, beam equation, then also we have, say, so when we are dealing with, say, yeah, plate equations, right? That plate theories, then we have this fourth. So you'll always see that there's always even ordered. So I don't know, this happens just by luck, or I don't know, it's some property, something to do with
Yeah,
symmetricity in nature.
totally.
That yeah,
That's
nature
a
always
really,
likes
really good question.
when
Really, really good
yeah,
question.
yeah.
I think it's about it's because see, yeah, that's a good question. I mean, whatever I'm saying, it's not an answer though. It's like
Uh,
say you have acceleration. Acceleration is
oh,
second derivative now of positions.
yeah. Mm-hmm.
So yeah, maybe that's. But how come why would structures have power four then, right? Like yeah, it's that's the thing. So
So, but you will see that they are always even numbered. I mean, always
good
even
question.
powered.
Really, really good question. Like why is this like everything is even power, right?
Yeah. So like you will always see whatever engineering problems that we solve, they always happen to be to the power some even number. Yeah. So that was how we distinguish between even and odd or Neumann and Euler boundary conditions. Sorry, Neumann and Dirichlet boundary conditions. Yeah. Now we're constructing to construct a test function space. So we need to have say V is equal to, it will consist of, say in this case we require L as we mentioned that it should belong to Hilbert space, again one step ahead. So H1 space, and then it should satisfy certain relations that U is equal to U naught, isn't it? U is equal to U naught. I'll just call it V just not to confuse you. This is like V is equal to 0 for all x, since this is a vector. So V is equal to 0 for all x is an element of omega at, there won't be any mention about t. So we always take test functions to be virtual, something like this. These are actually essentially virtual displacements. And as far as we recall, virtual displacements do not depend on time because it's taken at one particular instant. We are giving some virtual displacements to a system.
Okay.
So I hope you mean. I mean, this just follows from the in principles virtual work principle that say given some force F, and when we want to find some virtual work, then we give it some virtual displacement. So even if force vector will be a function of space and time, delta R will only be a function of space. So it means that given we take our system is at some time t, so we are giving the system some perturbations about its assumed stable state, some perturbations delta R. And this delta R is virtual in nature. Because it's virtual in nature, it's assumed that it takes place instantly. So it's like you have just stopped time and then you are giving the system a virtual displacement.
Yeah.
Yeah, this is like the crux here. Yeah. Yeah. Yeah, so that is why we call it virtual. Virtual in the sense it does not take place in reality. We are fixing the time and then giving it some displacements. And the counterintuitive part is you will wonder, but how can for a dynamic problem you stop it and then you are giving virtual displacement? Won't even displacement will also won't it also be a function of time? And that's the reason why we call it virtual, because it does not happen in reality. It's taken to be fixing time and then doing some arbitrary, you're giving it some arbitrary perturbation just to get some, and also this perturbations has to satisfy, this always has to satisfy the constraints, has to satisfy constraints. And that's the reason uh, this actually follows from the principles of classical mechanics, right? This has to follow from, this follows from there. So that's the reason. So test function, although the word sounds very complicated, right? It's essentially just virtual displacement. So there is where, yeah. So we are just what do you call? It's like trying to combine ideas from classical mechanics and then from functional analysis. We are just trying to, yeah, isn't it? So that's the goal here. So once we have defined our test function, so now what we have to do is, so now after this, what we'll do is, now we will multiply our say this equation, right? U vector dot V vector, and we will multiply equation with test function is equal to divergence of sigma. This you recall is a vector, right? So divergence of a tensor is a divergence of a second order tensor is a vector, and divergence of a vector is a, what do you say? So you must know this. I mean, not must. It's like divergence always reduces order.
Yeah, it's clear now. That should be a vector, right?
Yeah, reduces order of the operand on something on which we are operating on, and gradient always increases the order of the operand. So if you are say if you have a second order tensor, divergence will make it a vector. It will reduce its order by one. So second order means first order. And if it's vector is a first order tensor, so it becomes a scalar. And divergence cannot act on scalar because it becomes zero order. And you know there is nothing called zero order.
Yeah.
So that's the reason we cannot apply divergence on a scalar. Because scalar you cannot have divergence on a scalar. It's not possible. It's not possible, yeah. Now, and the thing is, now when you apply and gradient, if you apply to something, it will increase the order. Now, and the thing is, you can still apply gradient on a scalar, but the only thing is, scalar does not have a gradient. So if it's, sorry, I mean, not in that sense. So scalar, if it's a constant, it does not have gradient. So if you take gradient of a constant term, it becomes zero. Or in general, what does gradient do is, gradient always tries us to give the increase of that property, the direction or yeah, increase of the property. It tries to give us the maximum increase in the property possible. Just to make it more relatable, right? Just what do I mean here? So given any surface phi, when you apply a gradient at some point x vector, then it will always give us the local normal multiplied by some value, some scaling factor. So when you call about gradient of phi, right, it always gives us the direction of change, as well as magnitude of the change. No?
It gives maximum change, no? I mean,
yeah. So it's just like maximum change, yeah, maximum change possible in that space. So if the gradient happens to be living in Euler space, which means XYZ coordinates, then it will give us the maximum possible change in XYZ vertical space. And if you happen to have, say, gradient itself lies in, say, 4 dimensions, 7 dimension space, then in that particular dimension, what will be the maximum change? So that cannot be visualized. That's the only difference here. Okay, so returning again as to, so divergence of F, now we can multiply with V vector plus rho F vector dot V vector. And then now we have to integrate on both sides. with respect to d omega. Now, what we do is, now let's write it in indicial notation, then it will simplify our process. Otherwise, yeah. So this will be ui vi d omega, right? As per Einstein's notation, and then this will be divergence of sigma. So let's write something. So at first, sigma sigma tensor will be equal to sigma ij ei tensor product with ej. Now, when we take divergence, so the way divergence operates is, so divergence operation is always given by, so we'll have divergence. So it's like this is how it acts. Divergence of something, and then just put here ek. So when you act on this divergence of sigma, so this will be partial this sigma ij, then ei, ej, and then ek. Now, by the rules of tensorial calculus, so the one which is not in this tensor product, that gets converted into a dot product. So this becomes a dot product. Now you'll see this is this one divided by xk, and this becomes ei ej dot ek. So this is the what you call formula. Yeah, these are certain rules in tensor calculus. Yeah. Yeah. Then this becomes ei plus dot ej is this ei's and ej, they are just Cartesian basis coordinates, basis vectors. So this will become delta j k. Right. So delta j k, what it does is, wherever you find j, it will replace with k, or vice versa. If it finds k, it will replace with j. So here, since both j and k are available, so what we will do is, we'll just, in place of k, we'll put j. So this is what, now this is the divergence. And what you'll see is divergence is now acting along I direction. So it's like, it's a vector now, isn't it? Now you can clearly see that it's a summation involved over j, and vector, and then this this j will always be summed, and this will be one, and then there will be again summation over I. So if you write this, say you'll fix, say I is equal to 1, then this will be equal to x1 sigma 1 1 plus sigma 1 2 by x2 plus sigma 1 3 by x3, and this will be e1 plus like that. Then we'll have I is equal to I is equal to 3. So this, once we have this, now we'll put the expression here. So it will be partial by partial xj, right? And then sigma ij, and then ei, and then we'll and then there is this dot, right? So right now let's just keep it like this. So we'll put it vk and ek vector, because let's do some more simplifications here. And here in this case, we'll have, say, rho fi vi, we can have d omega. This actually, the thing is, this is so this operation will be, or this result will be valid everywhere in mechanics, in solid mechanics. So it's such a general result. So once we have this, right, now what we'll do is, this will ei dot ek will become delta ik. So which means that this will also become I. So this all goes away, and this just vi. Right? That's, now you see, right? Now there is the biggest. Now we'll have to do some major things here, some integration by parts. Now let's just divide into two integrals. This d omega, and this to be another omega d omega. Yeah. So this part is, we'll do integration by parts. So what we do is, let's write it in this form. This one, and we can also write this in terms of, we can use that Gauss divergence theorem or integration by parts. So what we'll have is, so what at first we will do this, we will say okay, I think another of the better way was to go something like this is equal to, we can have this sigma ij vi divided by partial with respect to partial xj minus sigma ij partial vi by partial xj. We can do this, right?
Yep.
It's like you take everything inside and then subtract the other part. Yeah, this is the what you call one way of doing things. Then you can see the first term here looks like divergence of something. So this you can write it as say
sigma v divergence, no?
Yeah. So it's like vi can be written in front, and
So
then it
from
becomes
Gauss
some.
theorem, it will be zero, no? Because it is. Let me see
No,
that.
so no, yeah. So from Gauss theorem, what you will say is, you will see that it becomes some.
It's a normal surface normal integral, right?
Yeah, exactly. Then it becomes something like that.
Zero.
So vi.
Sorry, it's not. Yeah, this is stupid. But
Yeah,
anyways,
sigma ij.
Dot n you should take, no?
Yeah, and then some ni, some nj d omega. This is like, we can do this right away. So it's like you just arrange it. So vi you put here, and then sigma ij divided by x, this one, right? And you just name this something to be, you can call this something to be, some say tj. So then it clearly looks like a Gauss divergence, some divergence going on, right? tj. So it's like divergence of t. And then this becomes t vector dot n vector after over partial omega. So then we can again put back our t as vi sigma ij dot ni. So it becomes nj. So that's what's going on. We will do this like tomorrow. We'll do this tensorial calculus somewhat in detail. I think once you master this, right? Yeah, it's very useful. Like these all basic things.
Yeah. True.
And the thing is, this is just the tip of the iceberg. Tensorial calculus is very vast.
Yes.
It's so vast. Like we just stop at Einstein's notations and all these Gauss divergence theorems, Stokes theorem. We don't go beyond that. And then Green's theorem again. Beyond that, we don't go. However, the thing is, tensor calculus starts from there. Actual calculus starts from there. Then we do derivatives over surfaces, manifolds, Riemann manifolds, differentiable manifolds. Then it becomes very interesting. Although it's messy, but it becomes much more interesting from there onwards. So that's So we can clearly see that we have made this now, and now it's the time to switch to a new page. So let me write everything here. Maybe just copy things from here, and then we'll make simplifications. And then paste. Okay. So now what we'll do is, we can even bring this downside, and then let it be like that. Now we'll just make a simplified approximation. So this becomes rho ui vi d omega is equal to partial omega vi sigma ij nj d omega minus omega sigma ij vi xj d omega plus rho fi vi d omega. Now here is some interesting things that are coming now. You recall that from quantum mechanics, what we had learned is that traction vector is equal to sigma into n vector.
Yep.
This we know, right? And in initial notation, it's Ti is equal to sigma ij and j.
Yeah.
So you see something going on, right? Here we can put
T.
Ti, isn't it? So you can clearly, so once we have put Ti, so this becomes Ti now. And then what we do is let's bring this term, this term on the left hand side. So it is omega rho ui vi d omega plus sigma ij vi by xj d omega, right? So is equal to omega vi ti d omega plus rho fi vi d omega. Now you can clearly see that where is this Ti coming from? This is essentially our, and again, this is over the surface. So this follows from boundary conditions. So recall we had prescribed certain boundary conditions, right? This boundary condition. Dirichle.
Yeah.
So it's like, so if you are not applying this one, right? If you are not applying any traction, so this term is zero naturally. So if T vector is equal to 0, then this term is 0 naturally, right?
Actually, yeah.
And that's the reason this is the reason we call this boundary conditions as natural boundary conditions. Because by the very process it becomes 0. The term containing natural boundary conditions becomes 0 by just doing the process itself. We don't have to define something. So what we see here is we had to clearly define our variational space with the Dirichlet boundary condition, that it has to satisfy Dirichlet conditions. For Neumann boundary conditions, it followed as a result of the process. So it's like that is how I learned it, and I don't know, but there are different approaches, like what Belitsko and all they will do is they will even add the boundary conditions as a part of the variational form using some penalty approach, and then they will reduce that. Okay, this is how we are forcing our boundary conditions, and then they sometimes cancel out to give the final weak form. But it's just like doing the same thing again. But yeah, anyway. So now we can clearly see that. Now we can say new slide, and then we can now write it back into its original format. So delete, yeah. Now we can write that in our form. I mean, in the way we want it. I mean, back into the vectorial form, weak form. Isn't it? So what we can do is this will be written now as omega rho u double dot vector dot v vector d omega plus. And sometimes you'll find some authors won't use this. They won't write this thing here. They won't write the what you call integral element. It's implied from the context. So you'll always find in real analysis books, right? They will write integral like this. So this is just to avoid some tough notations, right? It's just to say if it's partial, then it's implied the integration is the integral element is partial. Otherwise, we have to write something like this. It looks very messy. So that's why you'll find that many authors, they won't prefer. They will just write omega here. That's it. So, and for the second term, it becomes so sigma ij. I'll just simplify this term here. Vi by xj. This is actually, this happens to be a double contraction. So here I also gets summed up and j also gets summed up. So ultimately this term is a scalar. And you know that sigma is a second order tensor, right? So what we do is we will do some dot product such that one 10-second order tensor and the other again another second order tensor, they just are dot product in such a way that their end result is a scalar. So what we do is here is we can write this as sigma contracted with, and again in general for mechanics we always take sigma to be symmetric, right? So we can write this happens to be a gradient of v vector, so we can write this also, or otherwise and we'll get to this someday later during another session, that we can also write this as this is equivalent to sigma double dot the symmetric part transposed by 2. They are equivalent. Then this follows from symmetricity of sigma. So say if there is no magnetic couples or electromagnetic, some electric, some dielectric forces, right? Something related to that. If there are no such local couples in the body, then sigma, the Cauchy stress tensor, is going to be symmetric, isn't it? So by virtue of this, then we can write this sigma to be, and this written for a linear elastic problem, we can write it to be epsilon, and epsilon, you recall, is the linearized strain tensor. This as a function of v vector, and epsilon is defined as half of, right, grad of something, half of grad of something plus grad of something transpose.
Yeah.
That's the linearized strain tensor. So once we have this, so that's the reason we are able to just this is done. So we can write this to be, this we can write to be epsilon of v vector, and is equal to, and likewise we can write this to be rho f vector dot v vector from here, f vector dot v vector plus the boundary term, which is t vector dot v vector. I'll just skip this. I'll not write the integration element. So this is the weak form, and this is for linear problem. Or ideally, what I should do is, let me just write it grad v. This is for a general material, be it linear, nonlinear, doesn't matter. However, for linear problems, this can be written as epsilon of v vector. It's just because then we are using our what you call linearized strain tensor, or sorry, linearized virtual strain tensor, we call it, because since the displacement, the argument to epsilon is a v vector, and v vector is our what you call is the what you call variational function, right? So because of which it's called it, this is here virtual strain tensor, virtual linearized, or a better word is you'll find literature, it's also known as Cauchy strain tensor. So once we have derived this, I think now we can come back to the thing where we started. I'm going back to share. You can clearly see, right? Looks the same now.
Can't see your screen yet.
Cannot yet. Now?
Yes, now I can see.
You can see, right? This is the equation. Yeah. So this is what we wanted to derive. So I thought that why don't we derive it here, and to get a better view. So now, so this is what we have to do. I don't know. It looks like our time is out. Yeah. So maybe let's meet another session. I'll just stop recording.